Data crossing a network passes through equipment you do not own and cannot control: cables, routers, wireless links, all belonging to somebody else. Anyone with access to that path can intercept what goes past. And here is the point students most often get wrong, so let us settle it before anything else. Encryption does not stop interception. It cannot. The data still travels, it can still be copied, and a determined interceptor will still get hold of it. What encryption does is make the copy meaningless to whoever took it. So if an exam question asks what encryption is for, the answer is not that it prevents data being stolen or stops hackers getting in. It is that it makes stolen data unreadable or useless to the person who steals it. Answers that claim encryption prevents interception are not credited, and that is a very easy mark to throw away. 4 terms run through this whole topic, and marks go missing when they are blurred together. Plain text is the original data before encryption, readable and understandable. Ciphertext is what comes out afterwards, scrambled and not understandable. The encryption algorithm, sometimes called the cipher, is the process applied to the plain text, and the key is a value the algorithm uses to do it. Notice that the algorithm and the key are separate things. The algorithm is usually public knowledge. Anyone can look up how it works, and the security comes entirely from the key. That is worth holding on to, because it explains why the rest of this lesson is about keys rather than about algorithms. Encrypting is plain text plus algorithm plus key giving ciphertext. Decrypting runs the same route backwards. The first method is symmetric encryption, and the definition is short. The same key is used to encrypt and to decrypt. One key, doing both jobs. It is often called the secret key, and confusingly, it is also sometimes called the private key, which is a phrase you will meet again in a moment, meaning something quite different. So read questions carefully. The sender encrypts the plain text with the secret key and sends the ciphertext. The receiver decrypts it with the same secret key. That is efficient. The algorithm is comparatively simple, so it is fast and it needs less processing power. But look at what it requires. Both ends must already hold the identical key. So before any message can be sent, the key itself has to get to the receiver somehow. And that is where the whole thing runs into trouble. Let us watch that happen. Amira wants to send a confidential message to Ben using symmetric encryption, and somewhere along the network there is an interceptor copying everything that passes. First, Amira has to get the secret key to Ben, and the only route she has is the network. So the key crosses, and the interceptor copies it. Notice that nothing has gone wrong yet in the sense of a fault. The system is working exactly as designed. Next, Amira encrypts her message with that key and sends the ciphertext. The interceptor copies that too. Now count up what the interceptor is holding: the secret key and the ciphertext. That is everything needed to decrypt. The interceptor simply runs the decryption with the key it copied and reads the message in full. And this is the key distribution problem. Sending the secret key securely turns out to be exactly as hard as sending the data securely in the first place, which was the problem you were trying to solve. There is a second cost too. Every pair of people who want to communicate needs its own separate key, so the number of keys to manage grows very quickly. So symmetric encryption trades security for speed. In its favor, the algorithm is less complex, which makes it faster and lighter on processing power, and that genuinely matters when you are encrypting large volumes of data. Against it, the key must be shared with the receiver so it can be intercepted, and every pair of communicating parties needs its own key, so key management becomes a real burden at scale. Both of those disadvantages come from the same root. One key doing 2 jobs means that key has to travel. Fix that, and you fix both. Asymmetric encryption fixes it, and the idea is genuinely elegant. Instead of 1 key, you use 2, a key pair. They are different keys, but mathematically related. One is the public key, and it is given out freely to anybody who asks. It is used to encrypt. The other is the private key, kept secret by its owner and never shared with anyone. It is used to decrypt. And here is the property that makes the whole thing work. Data encrypted with a public key can only be decrypted with the matching private key. The public key cannot undo its own encryption. Read that again, because it sounds wrong the first time. The key that locked the message cannot unlock it. That one-way behavior is what lets you hand the public key to the entire world, including any interceptor, without weakening anything at all. So let us run exactly the same scenario again, with the same interceptor copying everything. Amira wants to send confidential data to Ben. First, Ben generates his key pair, a public key and a private key. He sends his public key to Amira across the network, and yes, the interceptor copies it. That is fine, and it is meant to be fine. The public key is not a secret. Amira now encrypts her plain text using Ben's public key and transmits the ciphertext. The interceptor copies that as well. So look at the haul. The interceptor has Ben's public key and the ciphertext. That is exactly as much as it captured in the symmetric case, every single thing that crossed the network. But this time it is not enough. The public key cannot decrypt what it encrypted, and the private key never traveled at all. It has sat on Ben's machine the entire time, so there was never a moment at which it could be intercepted. Ben decrypts with his private key and reads the message. The interceptor is left holding two items it cannot use. That is the whole argument for asymmetric encryption. And if a question asks why an intercepted public key is not a security risk, this is the answer. It can only encrypt, and decryption requires a key that was never transmitted. Put them side by side. Number of keys. Symmetric uses 1, asymmetric uses 2, a pair. Encryption. Symmetric uses the secret key. Asymmetric uses the public key. Decryption. Symmetric uses that same secret key. Asymmetric uses the private key. Is a key transmitted? Symmetric, yes. The secret key must be shared, and that is the vulnerability. Asymmetric, only the public key, which is not secret and does not matter. Speed. Symmetric is faster. Asymmetric is slower because the algorithm is more complex and needs more processing power. And security, symmetric is lower because the key can be intercepted. Asymmetric is higher because the private key is never sent. Notice that the speed column and the security column point in opposite directions. Neither method is simply better, which is why real systems frequently use both, using asymmetric encryption to exchange a symmetric key safely, and then symmetric encryption for the bulk of the data. 3 things to take into the exam, and all 3 are places marks are routinely dropped. First, never write that encryption stops, prevents, or blocks data being stolen or hacked. It does not. It makes intercepted data unreadable or meaningless. That phrasing is the mark. Second, name the key precisely. In asymmetric encryption, the public key encrypts and the private key decrypts. Writing just the key or swapping the 2 around loses it. And remember that the single key in symmetric encryption is sometimes itself called a private key. So identify which system the question is describing before you answer. Third, use the right word for the data at each stage. Before encryption, it is plaintext. After encryption, it is ciphertext. Calling ciphertext encrypted plaintext is imprecise and will not always be credited. Get those 3 right, and this topic is straightforward marks.